Okay, I actually released the study guide a day early yesterday because I got a request for that. So take note, anyone who needs anything from me at any point, if you want something that is not available yet and it would be useful to you, please send me a message and I will just do that because I don't want to waste your time. If you have the time to do something before it is up, I should respect that. So let me know if I can do that. I am happy to do that. So the fact that a study guide is up for our next exam means that it is a week from today. I do apologize for doing that to you on Halloween, but I felt like it would be better to do it on Halloween and let you have a little bit more relaxing night and weekend than try to have you come back on Monday and have that hanging over you.
That'd be
over that week. Yes, I agree. It would be spookier. It would be more in line with Halloween.
It would.
You think you're scared of costumes? What are you, children? I'm just scared of exams, like a real college student. But
It's spooky, but not fun.
right, yeah, it's supposed to be spooky and fun. So I want you to have a fun Halloween weekend. We'll get the torture out of the way before then. Then we have just the ongoing homework. Again, if you submit that by Monday, I can guarantee it gets turned around. Other than that, the earlier you submit, the more likely it is that you'll get it back by the exam. And we have the CYK project that is up, and I recommend you getting started and looking into that, because that is due in a couple of weeks. Any questions before we dive back into new content?
Could you draw a Venn diagram of like context-free, linear, regular, so we could just review like how are these types of languges related?
Yeah,
He's gonna whip up a bunch of considerations.
it's actually, yeah, in a later slide deck. Fine.
Oh,
Right. But once we've talked about other different languages, let's see if I can figure out exactly where that is really quickly.
I found it on Google at one point, and I was like, oh.
That quickly.
oh wow, oh okay.
In fact, yeah, it's not even that. So there's this and then there's that. These are two separate diagrams. So all we've seen so far is through L sub CF. So we have regular, deterministic, context-free, and context-free, and they're all subsets of each other. And we will see some other languages as we get into the rest of this that is coming. But we also see that we have regular, we have context-free, and now what we're talking about is deterministic context-free and what has a linear grammar represented for it. So though regular is all of that, it's embedded inside of all of that. If it's going to be regular, then it has to be linear. It has to be deterministic context-free. It has to be non-deterministic context-free. But there's a little bit of overlap and separation from deterministic context-free and linear, but they're all within the scope of non-deterministically context-free.
I think this one's a lot harder to process than the other one.
Yeah, it's because they're not quite as all subsets of each other.
I think that's because they just don't have linear on this
Well,
one.
I think there was like an example for each tier.
Yeah.
It's like 22.
Yeah,
Yeah.
But
especially because it's in black and white.
Yeah, that's all.
Yeah, so we'll eventually get back to that as well.
Okay.
That's a great question.
So that would be Chomsky hierarchy.
Yeah, the Chomsky hierarchy. There's literally 2 slides left of this. We're not going to go into being able to do problems on the pumping lemma for linear languages, but I want to represent when we have that linear subclass, what would you need to do with the pumping lemmas that we've talked about to be able to prove whether a language has a linear grammar for it or not. So we saw this distinction earlier, but we can make it between languages and not just grammars or strings. So a language is linear if we can find a linear context-free grammar for it. And tying to exactly that, the hierarchy we just looked at. This states that every linear language is context-free, so it's a subset of context-free, but not every context-free language is linear in nature, so it's a subset of non-deterministic context-free. There just was that separation between deterministic context-free and linear as well. Very much like the intro to every pumping lemma that we've seen so far, if we want to prove that a language is not linear, then we need to apply a linear pumping lemma to it. But it's not worth studying in quite the level of detail that we have everything else, because it is very similar to the context-free pumping lemma. One difference, and that is that UVYZ has to be less than or equal to M instead of BXY. So now we have to be able to get to the recursion and iterate the recursion in fewer than M characters, rather than get from the recursion back to the recursion and terminate the string. Same other constraint, and then pump. So it's exactly the same kind of logic. It's just that you attach yourself to a slightly different constrained rule.
This mean that the loop generates the whole string, or because you've got the host and the prefix.
Yeah, it's not that we have to try to terminate it. It's linear because from that starting position, we have to be able to kind of go from the start to the recursion and iterate the recursion. What this tells us with regards to the actual string is that getting to the recursion is what happens at the very ends. So UV YZ, instead of having a window that can slide, the BXY window, now UV is anchored to the left and YZ is anchored to the right. So that combination has to be less than or equal to M characters, which is a very interesting way to think about it. And then of course, X can be of arbitrary length. And X ends up being everything that isn't identified as UVYZ. And if you can solve context-free pumping lemma problems, you can solve linear language pumping lemma problems with fairly similar logic. So we focus for the rest of this course just on context-free. I don't make you memorize. I don't think there's a homework question on this. There's no exam question on this. So do not feel the need to memorize and be able to apply exactly this rule set anywhere else. I just want to talk about it because it is used in a few places in the world. But since it's not meaningfully different, I don't add it to the list of things that you should know how to do for the scope of this course. So yes, no homework or exam questions on the topic, just for context. And with that, we're through the last pumping lemma, at least in lecture. There's still homework and exams and office hours and other grossness, but at least for the lecture portion of this class, no more pumping lemmas. And I feel like that is a celebration that we can all have later tonight. Because it's Friday. We get to talk about a very important concept to the history of computer science, and turns out the most complicated state machine that we can construct. So we've talked about two major classes of state machines, and those have been regular state machines, DFAs and NFAs. We've talked about context-free, NPDAs and DPDAs. The last one we will discuss is Turing machines, because Turing machines have a profound effect. They are the way to represent everything that the modern computer can do in state machine form, which means that every program that you have ever written can be represented as one of these state machines. Every program that can be written via the modern computer can be represented as such. So we've seen regular languages, context-free languages. The only difference in terms of the state machine representation is we allowed for a stack. And you might start to think, well, if we wanted to prove that a language wasn't regular, a lot of those ended up being context-free. If we wanted to prove something isn't context-free, is there something outside of the scope of context-free? Despite looking at the Chomsky hierarchy a few minutes ago and seeing that there were things that were outside of that, but you might wonder what those things are and what they can represent. But are there other things that we could do to automata that we kind of talked about this, was it yesterday or the day before? Like, what happens if you just had an NPDA that you allowed for 2 stacks to go along with it, or 3 stacks, or a queue, or a hash map, or really any other data structure that you could think of? But taking this as far as we reasonably could, what is the most powerful automata that we could make? And what's fun is it turns out that any other data structure that you could have like this, 2 stacks, 3 stacks, a queue, etc., all of those, and I hinted at this last time, is not interesting. There's nothing interesting that gets added to the class of languages that could be represented by taking this idea of an NPDA and changing the associated data structure. There's no real value to that. That said, there is one class that's worth studying, and it is a Turing machine. I have a weird relationship with Turing machines. They're just the coolest things. So how we represent a Turing machine, it's actually quite simple. And the fact that you can make arbitrarily complicated programs, writing them in a high-level language, and they all can be represented with this very simple concept, continues to blow my mind every time I teach this course, every time that I engage with it in some capacity. I just think that it's profound. How do we store things on a Turing machine? It's just an infinite one-dimensional array in both directions, infinite number of cells next to each other, and they each hold a single symbol. So now instead of just a stack, there is an infinite tape. But it is a read-write tape. It's not just a read tape. So kind of like the stack was, we could determine what symbol was on top of the stack, remove it, replace it with something else in the stack alphabet. This infinite tape can be read from and written to at any position. There are no restrictions to only move left to right, like there were in the input string. We can move forwards, backwards, any number of times to do anything. We can have read portions of the tape, write portions of the tape. We can, as long as we associate the rules of when do we move left and right, when are we reading, when are we writing. That is everything that the modern computer can do. So no input file, no other storage. All that exists is this tape and a state machine that goes along with that tape. The input, the string that we're going to try to recognize, or the program that we are trying to run, all of that will be on the tape when the program begins. And we assume that what happens when the Turing machine begins is that we're going to begin at the leftmost character, and everything to the left of this is going to be blank, and the right of this is going to be the input. But from there, we can do anything we want. So Turing machine, there's a read-write head that moves along the tape and can read whatever is in the cell that the read-write head points to. It can write something at the position of the read-write head, and it can move left to right along the tape. The control unit is just a state machine, exactly as we have defined state machines so far. So there are states and there are transitions within that control unit. The rules of that control unit define what the read-write head does and which state it transitions into as it reads whatever is on the tape and writes to the tape. And that is the extent of the complexity of the Turing machine. It's quite simple. Of course, interacting with Turing machines is not so simple. Understanding and writing Turing machine programs is not that simple, but just the concept of what it is is incredibly simple. Formal definition of a Turing machine is very similar to what we've seen before. So instead of a stack alphabet, we will have a tape alphabet. Everything else is exactly the same. There is a special symbol in the tape alphabet called a blank. And this is kind of the equivalent of a null in computer science. It is something that exists, like it's a character that can be read, but it means that there is intentionally nothing here. Difference between there being nothing there and there being intentionally nothing there. So a cell can have nothing in it, but if it has the blank in it, then that tells us something. But yeah, other than that, we just have still, everything else is exactly the same. The transitions specify that what we're taking as input for a transition is a state that we are in and a symbol that we read on the tape. So that's what this left-hand side is saying. So a state and symbol that we read on from the read-write head on the current position, that's the input. That's what defines the input to the transition. The output to this is going to be a new state that we go to, a symbol that we write to the tape in its place. So you can read a symbol and write exactly that same symbol. Like think of it as a typewriter where you just type the same, type a character, somehow move back, type the same character, move back. It's just gonna look more bolded. It doesn't actually change what's on the tape, but we still need to specify that we write the same character that's already there. You can't write nothing. You have to write the same character. Then we also have a move either left or right. Note that the read-write head cannot stay in the same position in a base version of this Turing machine. You must make either a left or a right move as part of the destination of your transition, the incoming edge. Any questions on that formal definition? So here's an example of that transition. We start in state Q0. So internal state is Q0. The read-write head is pointing at this cell that contains an A. The internal transition, so something inside of the state machine, this is the transition that's specified, says when we're in state 0, Q0, and we read an A, then we should transition our internal state to Q1. We should replace that A with a D, and we should then move right. So now the read-write head is on the next character. We've changed our internal state, and we've written a character that didn't used to be there. If we wanted to do nothing to that A, we would have had to say write an A. You would not want to say write a blank or anything else of the sort. That would replace the A with kind of the null character or the blank character. Questions on that? It's the world's simplest, most abstracted computer, and the fact that this can do anything a computer can do is absolutely wild. You could write a Turing machine program that is Windows 11. You could do it. Theoretically, it's kind of like saying you could write Windows 11 in assembly, or you could write Windows 11 in binary.
It would be easier.
We know that we could do it. And anyone who is asked to do that, we will find them in a ditch somewhere before this is completed. Self-inflicted, I'm just gonna curl up in this ditch before the process is complete.
Well, it would probably be easier to write a program that converts the source code to the description of a Turing machine, right?
Yes.
Yeah.
Yes,
That's
that's why we study
already-
compilers. Yeah, exactly.
Yeah, there you go.
Yep. That's why we study compilers, because we want to know kind of the end goal and be able to map that onto the kinds of state machines that we've seen before. So that when we write a program in Java, what we're saying when we write a line of Java is what does that mean in terms of the actual underlying logic of what's happening at a CPU level. The internal state machine of this is your CPU. That is what a CPU does, is identify state and parse binary change state, determine whether we need to read to or write from disk or RAM, and continue. So it's just a more complicated Turing machine, but it doesn't handle anything that is actually more complicated than what a Turing machine could do. It's just more efficient at doing exactly that thing. So we have a CPU, and that CPU has finite memory. There is a state machine in there with a finite number of states, representing the program that this Turing machine is meant to do. We have unlimited capacity secondary storage, just like we did with an NPDA. It just forced that storage to be a stack. And this is an infinitely sized list that isn't zero indexed. So it's infinitely negatively indexed as well as positively indexed. All a Turing machine can do is pretty limited. Sense a symbol, decide what to do based on that symbol. We can rewrite the symbol, change the state of the control unit, and move the read-write head. It's so simple, it's genius. Is a Turing machine deterministic or non-deterministic? Yeah, there's no forking processes or anything that happens while we do this. There's always a specific transition that is defined in a particular state. We can talk about non-determinism in Turing machines. In fact, we will talk about non-determinism in Turing machines. But as stated so far, this is a deterministic process or idea. We can have at most one move for each configuration. Limitations of Turing machines. What can't this do? I already spoiled. I spoiled the last part of it, but kind of what is the limit of what a Turing machine can't do?
Shoot, I wanted to say something smart. I had heard I don't know, the decidability problem of like give it a program
Yeah,
that won't terminate. Could you ask it, will this program terminate? And
we will go into that in more detail than people want to.
Oh, really?
In a little bit, I will explain it. Everyone will be able to understand the undecidability problem. But yeah, that's one thing is the limitations of the modern computer are the same things as the limitations of a Turing machine. And understanding why a Turing machine can't do certain things will help us understand why a modern computer can't do those things. And that also will help you to be able to understand the kinds of programs that you can write or can't write, and why, when you attempt to write a program that does something, you won't necessarily have an answer to that. Undecidability is basically the subset of problems for where we could potentially answer yes, but we won't necessarily be able to answer no, because for some times when we would want to answer no, being able to answer no involves an infinite amount of time, or parsing an infinite number of objects, or something like that, where we can't ever say no, we just say we haven't said yes yet. And even though the program has been running for the last 8 billion years and hasn't terminated, we still don't know if it will terminate 5 seconds from now. We just know it hasn't terminated yet. Is it in an infinite loop, or is it still processing information in a way that will terminate? If that's a black box, we don't know. So those kinds of very theoretical questions are coming, and I eat them up. I love them. All right, so how do we actually determine Turing machine programs? There's an initial state for the Turing machine CPU. Just like we have before. We have some information written on the tape. Then we just go through the transitions that are defined within the control unit of the Turing machine. As we do this, the read-write head may be reading from and writing to the tape. And when the process terminates, what's on the tape ends up being our output. Either the program halts or doesn't, which will tell us accepts or rejects. Or halts in an accepting state, halts in a rejecting state, which tells us yes or no, halts or doesn't halt, which tells us can come up with an answer or it may spin forever. But the state in the control unit that terminates is gonna be called the halting state. It's a state that when we reach it, we say the program is over. And whether we went to that halting state from an accepting state or rejecting state will tell us whether we accept or reject what's on the string. And or if we halt and it's something with an associated output, then what's on the tape is that output. The idea is we convert the input that's on the tape at the beginning of the program to the output of the program by the time we go terminate. So that's how a program that takes input and produces output is going to translate to a Turing machine. The input is on the tape when the program begins, and the output is on the tape when the program ends. We just have to specify the associated transitions that convert that input to that output. So again, it works just like a program. That is the definition of a program, right? It converts inputs into outputs. So yes, transition function like an NFA, like an NPDA is only a partial function. We do not have to define every possible transition, even in a deterministic system, because it would be probably too much. Let's give you an example. Here's a Turing machine. Here's a tape. Starting in state Q0, read write head on the first character. Let's take a second and see if we can determine what this does. See if you can run this program in your head or draw out, use some kind of diagram to draw out what you think this does.
It'll flip all the A's to B's.
Yeah. It just turns whatever is on the tape, A's or B's, into B's. Going through it move by move. Starting on the left, we're in state Q0. We read the A. We're going to do this transition because the input that we see, we're in Q0 and the symbol that is on the tape is an A. So of these possible states, this is the one that we are in. So this tells us the output to that is to stay in state Q0, write a B at that location, which is how that A becomes a B, and then move right. So the read write head shifts one position to the right. So we end up in this state. Those are the associated changes. From here, we're in state Q0 with an A on the tape. We're still in this state. We're still using this transition. So we're going to stay in state Q0, write to B at the position of the read write head and move right, which gives us this position. Since this cell is empty, we can now recognize that via reading this special null blank character. So we are in this transition, or going to use this transition that says in state Q0, when we see a blank, we're going to transition our internal state from Q0 to Q1. We're going to write a blank, which allows us to continue to write nothing or turn a cell into nothing, or we have the ability to delete something via that. We delete it and move back left to this point and terminate. Since Q1 is a final state, when we reach that final state, we halt, and whatever is on the tape is the output.
The square is a null or blank character. What's the difference between that and lambda?
There is no lambda defined with this. We'll actually need that for non-determinism in this. So it's kind of like it's not a.
It means the same thing, but signifies something different.
Kind of. It's less, so lambda would say kind of it doesn't matter, or it's a transition that doesn't consume something, it's the empty string, as opposed to null or blank.
Oh,
So historically, we have kind of said on a lambda, which says don't read an input character, it's saying if we're reading something from right to left, don't move right. In a sense. And in this case, since we're reading it on the tape and can move left or right, and we have to move left or right, it's saying if we're at the position that is the, like, past the end of the input. That's not either an A or a B, or it's an empty string. I see how that confusion comes up. Absolutely. Does that make sense to everybody else as well? That's a really good point to clarify. So lambda will show up in some capacity, but yeah, in a Turing machine, blank signifies just a cell with nothing in it.
I don't know if they came up with these characters, you know.
Analyzing wingdings.
Yeah, what has it been used for? Scroll through Winding. Oh, they haven't used this one.
It's that theoretical computer scientist who's just, you know what, I really hate Greek. I really hate it. What other language can I use? Wingdings, excellent, we're good now.
Like who goes to wingdings before Cyrillic characters? Like
Oh, yeah.
how's Sindari?
I grew up in the 90s, so wingdings were the cool thing back then.
Oh, yeah. Those were kind of emojis before emojis.
Yes.
Yeah.
Yeah, the real nerds would be able to write ciphers and wingdings and show them to adults. I was not quite that cool. Just like with everything else, we could express a Turing machine using a transition graph. So with a DFA, we had states and transitions. With the NPDA, we had states and transitions, but the transitions got a little bit larger in nature with NPDAs. So they became triples instead of just the character that was on the associated edge. The Turing machine from the prior slide looks kind of like that. From state Q0, we can specify the associated transitions. Read an A, write a B, move right. Read a B, write a B, move right. Read a blank, write a blank, move left. How do we feel about that? Does that make sense or seem like it relates to the last slide's transitions?
And seeing this versus like the NPDA tuples. The only way I'd be able to tell the difference is like blank characters.
Yeah. So it's very similar. All right. All right. Given the following transition graph of a Turing machine, assuming the tape has an A and a B on it, what does this machine do? Yeah, this is a fun infinite loop in Turing machine form.
Yeah, because it doesn't even have to be in order. It could be in B and A on it in that order.
Yeah.
And then it could still also do an infinite loop.
Yeah, so we're in Q0, we read an A. Which transition do we do? The AA right, the very first one on the bottom. That transitions us from Q0 to Q1. We still have an A on the tape, but we moved right, so we're pointing at the B. We see the BB left transition. So we're going to make no change to the string and we end up back in Q0. We haven't done anything to what's on the tape. It's exactly the same. And we find ourselves back in the state that we started in. So we're just going to do exactly that logic over and over and over and over until the end of time. This sounds like a great homework assignment.
Never finished on.
Exactly. The only way to do this would be to recognize I should not begin this, because as soon as you begin it, you will never stop. There's something about the finality of life. It's like as soon as you enter an infinite loop, you're done. Life's over. You will die before it finishes.
It's called a 9 to 5.
It's like that's what all of you are here trying to get. What's wrong with society? learned from college.
It's true, if we consider philosophy too deeply, we start to wonder, what is the point of existence?
Yes, I consider this on a daily basis.
Yeah.
I find myself in philosophical infinite loops or philosophical ramblings in my own mind consistently. That's why I bring them to class and make jokes about them.
I have a really stupid joke after class.
Excellent. So as always, we can model configurations within a single image, what we need to be able to do something like the instantaneous description that we had before with the turnstile symbol, and that allowed us to show a walk through an NPDA. To be able to do this with a Turing machine, we need the following information. We need the current state of the control unit, contents of the tape, current position of the read-write head. So this helps us to be able to design what that might look like. So we start with some kind of the current internal state, whatever that happens to be, Q0, Q1. We need the current position on the tape, which tells us that this is where the beginning of the input starts. We obviously can't begin at the beginning of the tape because it goes infinitely in that direction forever. But eventually there's just no useful information out there. So this is the first useful information. If we could specify, here's what's on the tape that is not blanks up to the current position, and then everything that's still on the tape up to the end, and then there are blanks forever. Then we could specify, and this is way too small to see, I'll zoom in on it, a type of instantaneous description that is just a string that tells us the characters on the tape, A1, A2, all the way to the last character before the one that the read-write head is pointing at. Then we put the states that we are currently in, then the character that the read-write head is pointing at, and then all of the rest of the characters. That string tells us everything that we need to know about the current state of the Turing machine. The contents of the tape, the state that we're in, and the position the read-write head is in based on where that state shows up in the string. Anything unspecified are blanks. Questions on that representation? Does that map or make sense?
It's a lot simpler than most of the other, like you're saying with the turnstiles and stuff. It's a
Yeah.
lot simpler to just write this is a
Well,
string.
you will turnstile this.
Oh, well,
And that would, as we say, the next state after this, what happens when we make a transition from this turnstile to the next one, turnstile to the next one. But this is how you represent a particular state in that turnstile list of transitions. So again, we use the turnstile to move from one configuration to the next. So if we were going to model this associated transition from Q1 on a C, we move to state Q2, replace that C with an E and move right. The tape is already containing A, B, C, D, and the read-write head is on the C. Go ahead and denote that transition using the configuration syntax. What does that look like? So this should just be a single turnstile. You should have a string, turnstile, string. So here's what, this is where we are before the transition, and then we're gonna go through this transition.
alphabets.
Now, like, you know, which you might teach you would tell me, like, your A's look like U's and your U's look like A's, because I've never.
Oh,
full.
yeah,
Anyone need more time? Is it still working?
I'm good.
Hopefully we got this. Any questions on this answer? Or is this what everybody got? The string that we begin is A, B, C, D. Where is the read write head? It's on the C, so it shows up before the C in the string. And that state was Q1, so that's the state that goes there. At the end of it, we've moved right, so it moves past the character that used to be there, but it also rewrote that character from a C to an E when it did that. So all of that logic is embedded, and you can see how it's displayed in this string, turnstile string. We can see the embedded information from that transition in that. We've already kind of seen that it's possible to produce a set of instructions that puts a Turing machine into an infinite loop. We will talk about this probably in way more detail than people care to. But we'll try to make it fun as we do it. So what can we do with Turing machines? The answer is an absolute ton, but we're going to start by using it for the same kinds of questions that we have used other classes of languages for. So using them as language acceptors. They can do a lot more than that, but let's at least map it onto what we've already talked about before we really think about what else can we do with Turing machines. So we would want to write some kind of Turing machine program that will recognize a language. Given that we have a string on the input tape, we would want to write the associated states and transitions of the control unit such that we will halt and accept when the string that's on the tape is in that language, and halt and reject when the string is not in that language. So we assume that the string is written on the tape. Blanks are on every single space on the infinite tape that's not used by the string. What this means is it doesn't matter where the string is on the tape. It's infinite. Wherever it is, that's where we'll hone in on. We assume it starts in the initial state, positioned at the first character of the string. Then we will accept the string if we go into a final state and have halted. Within the string itself, there are no blanks. If there were spaces or something of the sort, they would not be blanks. They would be a certain space character that is separate from the blank, which is why I try to have the idea that the blank is more like a null. It is a character that is separate from the empty string or the empty character, or it's its own separate character that is null. If we allowed them, there'd be ambiguity between have we reached the end of the string and is there more of the string to come? And that way, if you did reach the end of the string and you had seen 10 million blanks on one side, is there more string out there? We'd have to go check. So the blank is a very special character that just represents the end of the part of these tapes that we care about. And you can rewrite some blanks into characters that matter if you need more output space than you had input space. But we never anticipate that there is input past those blanks because that creates that ambiguity that we would never be able to resolve without an infinite amount of time and processing power. We don't want to do that or have to do that.
So then could we could almost think of it as like, there's really just two blanks. There's like, it's like a null terminator, just at both ends.
Yeah,
kinda?
yeah, kind of bookends or null terminators on both ends of a string or something that, yeah, and since the read write head starts at the leftmost character of that, it doesn't matter what else is out there.
Yeah.
It doesn't matter if we're at position 1 or position 10 million, we're at the beginning. So for all intents and purposes, it is position 1 locally with respect to where this string is, or position 0 if you want to zero index it. So if W is not in the language, we need to indicate failure. We either need to halt in a non-final state or enter an infinite loop and never halt. And ideally, we want to halt in a non-final state, but we will find some problems where there is no way to halt in a non-final state. And the only way to indicate failure will be to enter an infinite loop and never halt. And that is the class of languages that we can't write programs for. And those exist. And we'll talk about what that boundary is in a bit. So let's spend the last few minutes of class writing a Turing machine program to accept 0, 0 star. This is the equivalent of just 0 plus, one or more zeros, and the associated language could be binary. So the alphabet, sorry.
I don't know. A rejecting final state in a,
You would just reach a point where you're complete in a, yeah, I see the point of the question. Yeah, because you're not like at the end of the string, so therefore you are done.
Yeah.
Yeah, so you would just, at that point, once you dedicate a new state for that. It's something that there's no transition out of,
Okay.
and you go to that state. It's kind of like a trap state in a DFA, except it's a halting state where you just, you don't define transitions out of it.
can I denote it like QF?
Yeah,
Wait, if we don't define a transition, oh, but then if we're in an accepting state, we didn't define a transition. Technically, we halt and accept, right?
we can, yeah, it depends on, yeah, we define kind of a halting state as just when we're done with the program, think of it like you reach the last line of a program and the program exits. How do we know to exit with flag 0 or flag 1? Exit it normally, exit it with an error. We reach the point where it's time to exit. There are no further instructions. Was it because we intended to or didn't intend to?
You don't need a second or a third internal state to denote accepting and failing. You only need one for failing.
Because we only need a partial function.
Because
The equivalent
because
of having
Q0
made a fail, if you just don't have a transition defined for it, it's the equivalent. So there's nothing wrong with making a particular failure state, especially if it helps you to visualize the problem or make it more of a complete function. But it's not strictly necessary for the representation of a Turing machine. So I leave it up to you. We will find that writing Turing machine programs, kind of like with NPDAs, especially as they start to scale in difficulty, it starts to make more sense to write them as groups of transitions specified like this, and less as actual state machine states. It makes even less sense here than it does before. But note that if this is binary, if we ever see a 1, we just reject anyway. So we should never even consider what happens when we see a 1. There's never a 1 in an accepting string, so they shouldn't remotely be part of our transitions. All we need to do is make sure that in Q0, we see some zeros, and once we see a blank, we move over. This is kind of 0 star though, not 0, 0 star. Yeah, I think we might actually need one more state for this. To be able to see the first one and then more, and then move to a final state. I think I've noticed this problem every time I teach this, and I still haven't fixed this slide. But yeah.
Easter egg for students.
Yeah. Yeah. So we do need a third state here. Read the first 0, read some more, potentially more zeros, and then move to acceptance. We'll come back to a couple more examples of this on Monday.
Why do you read blank on the second state?
Is it just anything?
It's
else?
to get to the halt and accept state, because if we halted in Q0, we don't want to accept.
What if you read one of them?
Then you halt immediately wherever that is. But the only transition that we define is as soon as we get to Q1, we accept, because we found the blank. So we just
Oh,
halt
I
from
see.
that point, there's no further,
It's the end of the string.
yeah.
But I'm envisioning that we don't accept ones in this, like in the transitions, as sort of like a, oh, you tried to call a method on an object that doesn't exist.
Yeah, it's kind of it immediately fails.
It's like throw an exception.
Yes,
Oh,
yeah. It's amazing how you start to look at this and you start to look at programmatic concepts, and I think that studying this theory actually helps you to figure out how do I write my own programs? How do I analyze my own programs, decompose problems into a program, because you've had a chance to think about it kind of at this deeper logical level. I find that it helps me a lot. If I think of a complex problem in terms of just object-oriented programming, if I think of it as a state machine and the associated transitions between these states of objects, that I can use the intuition of when I help people on homework problems in this class, that translates to designing my own programs.
This is exact, I've done a lot of like parsing strings and serial in
Yeah.
C, and this is exactly, it's like
Yeah.
just keep going until you find really.
Yeah, so it might seem like this class is incredibly theoretical and kind of abstracted from the actual day-to-day programming that you do, but the more you think about it, you will find how it's related and how it can help you be a better programmer. So yeah, I have office hours starting right now. If anyone would like any assistance with anything. Other than that, have a great weekend. Start CYK, and I'll see you on Monday.
you know, you're a machine, so.
Sure.
It's not-